Welcome back. We are in circular motion, universal gravitation. We're on worksheet 3, which is the universal gravitation portion. We're going to do number 10 here. Now, if you haven't watched number 9, go watch number 9 because it's almost the same thing. We're just solving for a different variable. But let's go do this. We got Callisto, which is a moon of Jupiter. Galileo, which Galileo, that's his first name. It's not his last name. Galileo Galilei is his last name. Anyways, in 1610, Callisto's got some mass. Jupiter's got even more mass. And average radius of Callisto's orbit is this. It's, the most orbits are not perfect circles. So if we use the average, well, then it's a perfect circle. And that's what we're doing here. So we're finding the period here. So the period is a big question mark. So anytime that I do anything like this, I make a picture. And I'm going to make Jupiter here, the red giant, you may say, or Jupiter. And the little moon of Callisto here. And I think to myself, hey, what do I know about this? Well, I know that there's a force of gravity acting on Callisto, and there's a force of gravity acting on Jupiter there. And these forces of gravity have to be exactly equal to one another. The law says that, and if we go and use this equation, that says that as well. There's some radius that exists here, and so let's go ahead and let's put that radius in. That radius is from there to the center there. And we know the radius, right? We have that radius right there, which is that guy. Cool, great. So what am I going to do? Well, I'm going to choose my system. So let's choose our system to be Callisto. Why not? Why? Well, because we're trying to find the period for Callisto, so that probably makes most sense. And now I'm going to go and I'm going to sum things up in the radial dimension. Yeah, we're still going in a circle here, so I have sketched the tangential dimension there. That's kind of a bad sketch there. And then the radial dimension going directly inwards and outwards. The thing going inwards is the positive radial dimension, outwards, negative radial dimension. So let's go sum up the forces in the radial dimension, since I only have forces in the radial dimension anyways. So what do I have? I got sum of the forces equal to m times a, as always. The left-hand side, I got the force of gravity, and force of gravity is positive because it's going radially inwards here. Okay, great. That's equal to m times a. I think about that and I go, force of gravity. Well, I don't know exactly what that is, but I know it's big G, the mass of Jupiter times the mass of Callisto divided by the radius between them squared. So yeah, you can use M1 or M2 or big M and little m, or just put subscripts on there so they're descriptive there. And then that's equal to m times a. Now think about that. What mass is this referring to? It's no different than any other problem or any other unit. You've made a system here. And so you've summed up the forces on your system. These are the forces on the system. And it's equal to the mass of your system, the acceleration of your system, right? It's always in relation to one another. So this mass here is the mass of your system. We chose that to be Callisto. So that is the mass of Callisto, and therefore the acceleration of Callisto as well. Okay, great. What does that mean? Well, that means that I can immediately go and cancel out these masses here because we can divide both by both of those masses. So that means the mass of this moon here doesn't even make a difference. Interesting. Furthermore, I recognize that this is an acceleration that is a centripetal acceleration, and so that's the same thing as a tangential velocity squared divided by the radius, and so I can go ahead and I can put that in there. So let's go do that. Yeah, big G is multiplied by the mass of Jupiter divided by the radius squared is equal to the tangential velocity squared over the radius. Now, what are we trying to find here? We're trying to find the period. I don't even have the period within here, but you're thinking to yourself, I've done this multiple times now. Tangential velocity there, I'm not given that either, but I recognize that the tangential velocity is going to be related to, well, how far it's going, 2 pi r, divided by how long it takes to do that, which is the definition of a period, the time it takes for something to go and start repeating that motion there. In this case, going around there and then starting to repeat going around there. So that is the period there. And so now I can go and take that and I can plug that in for there. So let's go do that. Got big G, mass of Jupiter over the radius squared is equal to, now square everything, take that 2 pi r over t and you got to square that whole thing. So you get 4 pi squared, don't forget about squaring that pi, that's an easy one to forget, r squared divided by t squared, and then r's in the denominator still. notice I kind of skipped a step there. This whole thing is in the numerator, but that's the same thing as just shifting that t squared down to the denominator there. Just doing rules of fractions there. And so now let's go ahead and let's see if we can clean some things up here. Well, what do we have? We got r squared here and a single r down there. That's nice. Doesn't look like anything else is going to cancel out there. I need to solve for t squared. So I'm going to get t squared by itself there. How am I going to get t squared by itself? I'm going to move t squared to the left-hand side, and then I'm going to move all of that stuff to the right-hand side. Let's do that together here. What is that going to look like? Well, first, on the right side, I got 4 pi squared times r to the first power. Now, I got r to the first power, but I'm going to move this r squared over here. So I'm going to multiply both sides by r squared, which is going to give me r squared times r to the first. That's r cubed. Okay, great. What else am I going to do? Well, I'm going to move t squared over to this side. So t squared is going to show up in the numerator there, which is nice because I'm trying to get t by itself. But I need to get this stuff out of here too. So I'm going to divide by my g value. And I'm going to divide by that mass of Jupiter there. Now let's make sure that I didn't forget anything here. So let's see. I multiplied by t squared to get t over there, and that's in the numerator. That's good. I divided by the mass of Jupiter. I divided by g. Great. And I moved the r squared over to the numerator there. Yes, I did. Okay, great. Now it looks like I did everything there. And so now I go, oh, I don't want t squared. I want t by itself. So I got to take the square root of both sides here. And so that means that I'm going to have t is equal to the square root of that whole thing there, 4 pi squared r cubed over big G mass of Jupiter there. And now we could put in all of those values if you wanted to. Well, you could just put them straight into your calculator, but I'll write it out for you just in case here. The radius, what was the radius? I don't remember. 1.883 10 to the 9th. 0.883 times 10 to the 9th. And I got to cube that, don't forget. G, I'm just going to leave that as G. It's a constant there. It should be programmed into your calculator anyways. The mass of Jupiter here, 1.898 10 to the 27th. And that is not squared there. And so now I'm going to grab my calculator and I'm going to do all of that stuff. So do it in one line here, make things nice and simple. 4 pi squared, I'm always following order of operations, times 1.883. I use my shortcut things here because that makes my life way easier. I clicked math and I'm going to go and do the power of 3 there, which makes that look way nicer too. Divide that by everything in the denominator. I have multiple things multiplied there, so I'm going to need to put that in parentheses. I have G already stored in my calculator, as you should too, because why would you want to type that every time? Times 10 to the 27th power there. And that's it. And I get 1,442,926. 1,442,926, and then some change there, right? 926.892. That's a time value there, so that's in seconds there. So I'm going to put in some commas there for you. And so we know that that's in seconds because that's the SI unit for any time value, and I only had SI units here. I can go back and double check all that, but that's only SI units. I go back and double check that. Did I square the pi? Yes, I did. And did I cube that thing? Yes, I did. Okay, cool. Looks like I probably did that correctly. And we look at the solution, and yeah, sure enough, hey, cool, yeah. And I could even get that into hours and days there if I wanted to. So that's it. Have a beautiful day. See you later. Bye.